Hello everyone, today we are going to talk about another topic. So let's shift the gears to a different topic now. We will talk about spacecraft design project phases. So far we have talked about the different subsystems of the spacecraft, about the environmental, analysis, the thermal environment of the spacecraft, heat transfer aspects, mechanics of orbits, and different types of thermal architectures. So here we want to talk about the design phases, so how we actually approach the design project. So what we will talk about today is not necessarily related to spacecrafts. It's been tailored for the spacecraft, but it can be applied to other design processes and design projects as well. It is also in the domain of like project management, so it will provide you a broader understanding of these design project phases. And I also should mention that even though I will finish, for instance, this topic in one lecture, but this is equivalent to more than one lecture of the class time, because here I speak faster and basically there is no chance for question and answer and back and forth. So this usually, it's equivalent to more than one lecture hour. So you may need to spend additional time in order to understand the entire details. Okay, so the reading sources and references for this particular lecture, I have used mostly the reference one and the associated chapter for this lecture. So the spacecraft project can be categorized in multiple phases, as I said, similar to many other project phases, like for different projects, not necessarily a spacecraft. So the phase one is the concept definition phase. So we want to understand the feasibility of the concept. We want to develop the concept and see whether it is feasible, how it's going to look like. Then we need to go ahead and validate the concept, see whether it's feasible. Do you want to go ahead and execute this project? And if the answer is yes, if it's positive, then the full scale development phase, which is the most important phase of the project, will be taken place. And once it's designed and ready, then we do have the operation phase, which we will continue to monitor the performance of the spacecraft and troubleshoot, learn lessons for the future flights, and so on. We also should pay attention that not all of these phases may be necessarily and accurately and one by one be followed. It depends on the size of the institution, the size of the company, which is actually performing this project. So oftentimes, let's say in startup companies, because of the limitation in resources, so the concept definition phase may be very short, or it may be done differently, or the validation phase may be combined with the concept definition phase. So this is like the four like conventional and standard phases of a spacecraft project. So for instance, you should expect that if NASA wants to execute a project such as the Artemis project going back to the moon, so you could expect that NASA has already followed some of the phases of the Artemis project, and it's going to follow basically these four stages. NASA has like a large and established organization. So when it comes to the thermal design aspect, So the thermal design analysis process overview. So the thermal design will be a part of the design phase. So the design phase actually includes all the design of all subsystems, and one of those subsystems is the thermal subsystem. So as you remember, we do have multiple subsystems, like from the structure, like the communication and data handling, attitude control subsystem in the case of a spacecraft, like propulsion subsystem, launch, for instance, subsystem, and power subsystem like batteries and so on. So the thermal design is one of these subsystems. So the thermal design process is a combination of design selection and supporting analysis. So the thermal engineer or the thermal engineers must either select and also provide supporting analysis and design for the thermal subsystem. So the selection of the selection of a viable thermal design approach may become almost intuitive for an experienced thermal engineer. So let's say it's for a standard satellite. Then most experienced thermal engineers know that they would need to go and choose multi-layer insulation. They will need to use like what kind of optical coating for the radiators, well, and also heat pipes. So it could be, as simple as that. However, for some other spacecrafts which are going to follow multiple phases in their mission, for instance, like for moving to the moon, we do have multiple phases from the launch, orbiting the Earth, and then fly by, going to the moon orbit, and then orbiting the moon, and then landing on the moon. So these are very different thermal environments. So the solution is much more than that. So it involves a lot of more effort. So the detailed thermal analysis are required to verify and refine the design. So once the design is proposed, for instance, in the concept validation, in the concept definition phase and the validation phase, then in the next step, it has to be actually verified and refined in order to make sure that it can actually perform the requirements. So a wide range of thermal control hardware and techniques is available, and which we have actually studied in previous chapters, like from heat pipes, fluid loop, insulations, coatings, how to design radiator, louvers, and so on. Phase change materials. So the spacecraft system requirements to minimize weight. So these are basically the requirements that every subsystem must follow, the guidelines. So to minimize weight, cost, test complexity, while maximizing reliability, are usually served best by keeping the thermal design as simple as possible and by avoiding the use of active components. So the thermal design or the thermal engineer should start from the simplest thermal architectures. Simplest, which means that the one without like using passive components, such as like as easy as insulators and also optical coatings. And then if required, they should go toward like more complex systems, such as then heat pipes, and then after that fluid loops, just radiator panels, as a part of the structure, and then go ahead if needed, use deployable radiators and so on. So the philosophy is to start from lightweight, low cost, simple, and easy to integrate thermal systems. And if it's required, then other solutions should be tested. Even sometimes the solution may not exist for a kind of emission which has not been done before, then it may be required to actually develop and test a new thermal solution. So let's start with the concept definition phase. So that's the start of that's the kickoff of a project. So if we want to actually perform, if a company, for instance, or if a group of strategists, for instance, in a company want to come up with a concept, so the concept has to be defined carefully and clearly. So that in order to basically kick off the project. So that's the concept definition phase. So this phase usually consists of a customer-sponsored trade study examining the feasibility of various approaches to meet the intent of a concept. So again, this depends on the size of the organization. If we are talking about NASA, then NASA may want to basically sponsor a trade study on the Artemis mission going back to the moon. So then NASA would be the customer, and then NASA may want other companies in order to perform this concept definition study. Sometimes, for instance, the NASA may define, or a large company may define may initiate the concept, and then some internal departments of the company may go ahead and work on that particular project. So in other words, the customer and contractor may be actually the same company, two different sections of a company within one company, or they may be actually two different entities. So here we said that to meet the intent of a concept. So the intent of a concept may be just a qualitative description of a potential mission. So the intent may be, for instance, okay, we want to explore Mars, or we want to go back to the moon. That could be the intent. So the role of the thermal engineer in this phase of the concept definition is to evaluate alternative approaches to spacecraft thermal control. So in this phase, it's just considering, alternative approaches for the thermal control. It is quite, qualitative. It doesn't have to be it's based on parametric studies or just feasibility studies to see whether it's doable. Let's say the mission is that, okay, we want to go and explore the surface of the sun. I mean, then the question is that, okay, so how a spacecraft is going to approach the sun and how close it can approach the sun. Is this feasible at all? Or, I mean, how far it's possible based on the intensity of the solar irradiation and so on. So then considering the thermal requirements of all vehicle elements for all mission phases. So as I said, so we need to look at different phases of the mission and the thermal requirements. For instance, if for going to the moon, the mission consists of multiple phases: the launch, orbiting the Earth, flyby to the moon, and then orbiting the moon and landing on the moon. Moon has days and nights, right? So the mission, depending on whether the mission is going to be done during the day of the moon, which is 14 days, or it's going to actually cover the day and night of the moon. So the thermal requirements are quite different. So so we need to see whether a thermal solution that has been designed for the days of the moon, is it also flexible enough to address the thermal requirement for the night of the moon, because the temperature difference and fluctuations can be quite large. So this way we can actually evaluate the concept and see if it makes sense. The concept definition means that we need to define the concept and see whether it makes sense. Is it doable or not? So the engineer may quickly see that some standard thermal control techniques may suffice if it's like a simple mission. Other elements may need parametric thermal analysis to assess their system level impact resulting from size, weight, power, or complexity. So some answers may be found quickly, but some other answers may need like additional analysis. But the analysis is at the system level. At this stage, the engineer is not going to design, for instance, the size of the heat pipes or the thickness of the insulation, or these details are for the later stages. At this stage, it's like a general uh, parametric thermal analysis in order to see whether the process is feasible, or if the weight of the system, the power, the required power, the complexity, how we know we can, is basically to picture the entire system and show it in the document so that the executives, the customer, can decide whether they want to do it or not. So in this phase, the concept definition phase, a baseline spacecraft design is created. So a baseline design means to have the big picture, the idea how it's going to look like, the weight, the power, probably the cost, this kind of things. So from the parametric analysis of each subsystem engineer, so each subsystem will be actually conceptualized by each subsystem engineers, and then it will be put together. So ideally, this design represents an optimum balance between the competing requirements of different subsystems, including the thermal subsystem and overall system mass, volume, reliability, and cost. So this is a kind of collaborative work. So different subsystem owners need to work together in order to come up with the optimum, for instance, mass of the system, reliability, cost. So, and the design of one subsystem may significantly influence the design of another subsystem. So it has to be done collaboratively so that the whole, and if one of the subsystems does not consider the needs of the other subsystems, then it will fail. So the spacecraft will not work properly. So in this phase, the concept definition phase, assessment of the thermal subsystem is required as one of the subsystems by reviewing the state-of-the-art technologies. This is always very important. Stand on shoulders of giants. So we need to see what is out there. We need to study the state-of-the-art technology so that we don't have to reinvent the wheel. Some of these thermal technologies will be mature, like the optical coatings, insulations, heat pipes, but some of them may need additional R&D and development tests. So the level of maturity of a technology is defined by the technology readiness level. So the technology readiness level we will talk about in the next slide. So the higher the technology readiness level, the better, because the technology will be more reliable and it means it has been tested. So this diagram, and this is the reference, so this diagram shows the technology readiness level, TRL. It starts from level 1 to level 9. So level 1 is just basic principle observed and reported. Let's say someone comes with an idea for a new thermal system, and then they just communicate the idea in the form of a patent or in a paper, in an article, but that's just the principle observed. So it hasn't been tested. Then the next step would be the concept is formulated. So it's been modeled and shown by like mathematical equations. Then the level can become more mature and mature until we get to level 9, where the actual system has the actual system is flight proven through successful mission operations. For instance, that system has been already used in one or more satellites or spacecrafts. So that's the best level, TRL9, which is flight proven. So in between, we do have different levels of TRL, and the higher the level, the better, because it's more reliable and it's been tested. So essentially, it's better to start from technologies or thermal solutions with higher TRL, and then if they are not adequate for that particular mission, then we would need to go to lower the concepts with lower TRL, and then continue to the development to bring the readiness to the higher levels. So at the onset of a concept definition study, the technical team must be prepared and must do the following items. So plan the depth of support to be consistent with the study schedule, funding, and so on. So oftentimes engineers and program managers work on multiple projects, and then maybe a new project is assigned to them, like the concept definition phase of a new project may be assigned to a group of engineers who already have multiple other projects. So they need to therefore plan accordingly, plan the depth of support to be consistent with the study schedule, funding, etc. So they want to basically be prepared how much they can support and what is needed, what's the schedule, how much funding is needed, and so on. And they should understand the overall study milestones, how easy or difficult it is, and gear effort accordingly. So for instance, if the project is something quite new, a new idea, and it requires more effort and funding, and it is challenging to address some of the milestones, so they need to be really prepared and put effort accordingly. So if available funding and other resources is not sufficient to provide meaningful support to the study, this should be raised with the leaders so that the leaders know that additional funding or like additional technical support is needed, so that the company can go ahead and hire new people or dedicate new funding, more funding, and so on. And any issues that cannot be adequately addressed because of funding or schedule limitations must be documented. So this stage, after all, is the most important stage of the project, because if the stage is not done properly, and if a project is not feasible, or it's actually too difficult, is far-fetched, then if it's approved while actually it should have not been approved, then a lot of money and then funding and time may be spent on a project which may eventually fail because of the lack of sufficient work on the concept definition. So we can mention about the fact that, for instance, startup companies, so roughly like 1 out of 10 startup company will survive, perhaps because the initial ideas that the company has been established based hasn't been studied thoroughly, so that at the later stages, the company may face, challenges and then cannot continue their mission. Okay, so now let's talk about the validation phase. Once the concept has been defined and a feasibility study has been done, and then the overall shape of the spacecraft, different subsystems, the mission has been defined, then now it's the time to validate or to review this concept definition and come to a conclusion. So this means that what do I mean by come to a conclusion? It means that so once this phase one is complete, the design concept documents are reviewed by officials and the decision is made on whether to proceed or not. So officials means essentially people like leaders, executives, people who run the company, people who actually decide about the direction of the company, the budget, and so on. So the officials may be like, the officials could be like the customer, or that the officials can be like the executives of a company. So if positive, the program enters a validation phase. So the customer team, so before this, so when we say that, for instance, reviewed by officials, it means officials and their consultants, their advisors, people who help them to actually make the right decision based on the concept definition. For instance, depending on what is given in the previous phase regarding the challenges, the milestones, and the cost, the budget, then the company and the market, for instance, if it's like a private company and they want to develop a product, so they need to see how challenging is it to develop the product, and what is the market size for this product, and so on. In the case of the spacecraft, so space projects are mostly sponsored by the governments like NASA, ESA, but recently we know that many private companies have entered the race, and these private companies actually work based on the market and benefit. So that's why it is more challenging for the private companies to be able to initiate or focus and invest on projects that are profitable. So if positive, if the company wants, if for instance it's decided to go ahead, the program enters the validation phase. So the concept definition is reviewed and they see that, okay, so we want to do it, it's doable, we like it. Then what comes next? So the customer team, for instance NASA, which represents the US government and the US people, so the customer team generates a description of their desired system by refining and choosing technologies of the concept phase studies based on cost, schedule, and so on. So in the concept definition, so multiple recommendations may have been made. So the customer, based on that recommendations, can go ahead and refine or choose technologies given in the concept phase. So a system requirement review, SRR, so a system requirement review in terms of the entire spacecraft, is then held to reach agreement between customer and the contractor personnel to what the top level requirements will be. So the customer may be, for instance, NASA, and then the contractor may be a company which has been hired as consultants or advisors, or the customer could be like once part of like executives of NASA, the management, and then the contractor could be like the engineering department. So they need to basically do a system requirement review in order to define and specify the top level requirements. So top level requirement means what is essential for the mission. For instance, whether it's gonna land on the moon or it's gonna orbit the moon, whether the spacecraft is going to come back from the moon or we can just discard the spacecraft on the moon. Whether it's manned, well, of course, if it's a manned mission, you cannot just let the spacecraft remain there. But if it's unmanned, you can actually just leave the spacecraft there on the surface of the moon. And any critical technology questions must be addressed by tests at this stage to make sure that, early on, to make sure that if there is something critical, it should be addressed to make sure that it will work. And a system design review, after the system requirement review, a system design review may be held to complete the validation of the system design. So the end result of this phase will be a request for proposal. So once the documents of the concept definition phase have been reviewed and approved, and part of it have been selected in order to clearly define like the mission, then a request for proposal has to be prepared with the customer issues to industry to execute the plan. So far it's been like a feasibility study, but then documents have to be prepared, which that document is called a request for proposal, if the project is going to be done externally, right? So if it's going to be done internally, then this stage may be different, because if it's going to be done by, if it's been defined by NASA and then it's going to be done by another section of NASA, then it is kind of internally. So the process should be and will be easier because it will flow internally. But let's say that, especially with current projects like with the Artemis project, the program of coming back to the moon, it's been done this way. So NASA defines different stages or different phases of the program, and then prepares proposals, and usually private, small or large or medium-sized companies bid on these proposals and get the contract. So NASA actually, instead of doing most of the work in-house, now it's sourcing out the work in order to get involved like the private companies as well. So the end result of this phase will be a request for proposal, which the customer issues to industry to execute the plan. As I said, it's not only related to a spacecraft. So this can be like the project can be like building or constructing a new bridge on River X. So the same process will be repeated. So in some cases, all parties mentioned above, like the customer, contractor, industry, may be different part of an organization or company such as NASA. So we do have the customer and then the contractor, which has done the consulting work, and then an industry like a manufacturing company which has manufacturing capability will go ahead and actually manufacture, engineer, and manufacture the spacecraft. So these three or more different sections may be just in one organization, one big company, or the customer may be NASA and then the contractor may be like a different company or another part of NASA, and the industry may be different. So you should keep that in mind. So the request for proposal, RFP, it's a package. It's like a document. It's an official document, will become available to those who want to bid. It includes basic information such as schedules, instructions for submitting a proposal, The technical statement of work, which is a top level technical document. It basically says that what's going to be done and what is required to be done. System and subsystem design specifications. So as much as possible, as much as they want. So the request for proposal doesn't mean to provide all details about the spacecraft, because many details are up to the industry to figure out, but the proposal should actually tell what is going to be uh, built and what's the mission. So applicable specifications and regulation compliance documents. If it's like it's a US project, then it has to follow NASA, perhaps some military standards. And the contract data requirement list that we will talk about in the next slide. So these are the components of the request for proposal document. So what is a statement of the work, which is a part of the proposal, SOW? It is a list of tasks to be performed by the contractor or by the industry. Industry is the contractor, so such as the thermal analysis, trade studies, tests, and so on. So basically it will list different subsystems and what should be done for each subsystem. So the SOW is part of the legal contract about what the contractor must do. So a contract data requirement list is a list of applicable specifications and compliance documents which will be included with SOW. And SOW also contains the system subsystem design specifications. So some of the, not all of the specifications. So specifications for the design of each subsystem, including thermal control, may or may not be included depending upon the degree of control that the customer wishes to exercise over the contractor's design. For instance, the customer may include it in the proposal that the spacecraft must use, for instance, this particular type of thermal control. For instance, it must only use heat pipes. It must only use passive thermal solutions, not active. So this can be included or not included. If it's not included, then it's up to the contractor to decide what's thermal subsystem is the best solution to proceed with. And oftentimes there is usually a debate about what subsystem, what thermal solution is the best. So it's not like it's not that clear that what should be the right approach. So therefore the customer may just keep it open and leave it up to the contractor in order to decide what is the best solution for a subsystem. It becomes more important when we think that each of these subsystems are actually interrelated. So there should be some level of flexibility between how the things should be done to make sure that all of these subsystems will do their jobs properly. So the thermal aspects in the state of work includes the following. So a requirement to keep all component temperatures within the allowable limits. So this is kind of obvious. So this is the requirement that all equipment must operate at the allowable limits. Emphasize on the simplest, most reliable flight demonstrated technology. So high TRL, technology readiness level that we talked about. So this document says that, okay, we prefer that the contractor uses actually components with high TRL, something that has been proven to work before and does not easily fail, and therefore it's reliable. And it's simple. The simpler the better. In technology, it's always better to use simple things because you don't want to complicate the things. And if something can be done using simple things, it's much better. Passive is better than active. Simple is better than complex. And it is emphasized that there should be no single point failures in the thermal subsystem. So that it means that a single point of failure is a part of a system that if it fails will stop the entire system from working. So the document emphasizes that the contractor should design a thermal system which is not a single point of failure, or any part of it is not a single point of failure, meaning that if, for instance, a part of the thermal system fails, it does not result in the failure of the entire spacecraft and entire mission. There should be a backup solution. So nobody wants to have a single point of failure in the system in any design, in an automobile. So you really don't want, well, of course, in the case of automobile, for instance, if you get a flat tire, then it's a single point of failure because you cannot, drive it. But it's not, you can just, have it changed or have it towed. But in the case of an aircraft, in the aircraft as well, in the case of like a spacecraft, it's not that simple. If something happens, oftentimes it is not possible or it's very difficult to have it fixed. So it really depends on the mission, depends on the requirements, so that the appropriate technology can be used. So the thermal aspects in the SOW regarding it also includes compliance. It seems that the word is wrong. With military, NASA and other organization requirements, if it's in the United States. So it has to comply the standards. A design that is predictable. So the customer asks the contractor to provide a design that is predictable by thermal analysis and verifiable by ground tests. So if the engineers provide a solution, they should be able to actually demonstrate that it will work. Because once the mission has started, in the middle of the way, if it fails, then it's too late. So identification of key trade-off studies required. So this statement may ask the contractor to provide trade-off studies. For instance, they may want the contractor to perform analysis to compare multiple thermal solutions in order to choose the better one. Identification of key development and final verification tests. So if a thermal solution has to be developed based on the concept definition phase, then that has to be clearly stated here so that it clarifies the development method for that technology. So then the customer sends out the request for proposals. Multiple, let's say, private companies or maybe government entities, bid on that proposal. The next step is to evaluate the proposals and choose the best one. So again, this is applicable to any other project, not only a spacecraft. So the proposal evaluation phase has in like this phases. So a typical proposal submitted by a contractor. So the contractor that bids on a proposal, it usually consists of these parts: an executive summary of the proposal, The technical part, so the details of what they want to do in terms of the engineering part, management part of the proposal, how to manage the project, and a cost section, budget section. So how much is going to cost. So to the customer, cost is very important. So the first thing that they look at the proposal is that, oh, let's see how much is going to cost, right? So if the budget is the cost is too high, even if technically sound, the customer may does not pay enough attention to the proposal. So the cost is important, and all of these are limited to a certain length. So it's usually told the people who want to they want to respond to a proposal to write it within like limited pages with several sections. Okay, then a team. So let's say multiple responses to proposals have come in. So then a team of the customer personnel is assembled, representing a wide range of technical disciplines to evaluate the proposals. So let's say multiple responses have been given to NASA, then NASA assembles like at least one representative from each subsystem so that everybody can understand the proposal from different, like electrical engineers, computer, software, mechanical, structural, thermal, like communication, RF. So all of these must be in that group in order to be able to evaluate the proposals. So any thermal control issue affecting other spacecraft subsystems should be discussed with the team members evaluating other team members evaluating these subsystems to make sure that they are aware of the impacts. So sometimes when the responses to proposals come in, so it's possible that the company has not considered some aspects. For instance, they may have like underestimated the impact of the thermal control. They may think that thermal control is like not a big deal, it can be taken care of, but then if that part has been neglected or ignored, so it may result in the failure of other subsystems. So if this is seen in the response to the proposal by the thermal engineer or by all other engineers in the group regarding their own expertise, this has to be raised and discussed to make sure that when actually the contractor will perform the project, they will do it properly. So the reviewer must ensure that what the contractor has written demonstrates a sound understanding of what is required to develop the thermal control system on time and within budget. So if for instance the contractor has underestimated the thermal control and think that it's very easy and it doesn't take time and budget, it can actually raise a red flag if they think that something which requires some amount of time and budget. So if it's ignored, then that's a red flag. That then tells that the contractor may not be aware of all aspects of the technical design. So in order to select the best proposal at the conclusion, one or more contractors are selected to continue into the full-scale development phase. So, like if budget allows, actually more than one contractor can be chosen. Let's say in the case of the Artemis program, to go back to the moon, NASA has selected 2 or 3 private companies to deliver payload to the surface of the moon. So the reason that they have selected 2 or 3 is that if one of them, cannot do that, or if one of them fails, at least the other one can do the project, or by competition, or by like I mean, if budget allows, that can be done. But in some other cases, for instance, if the proposal is on to construct a bridge, of course you can only select one final contractor for this purpose. So, all right, so then the full development phase, it's actually when the work is done, when the spacecraft is going to be designed. It has two phases: preliminary design review and critical design review. Now, up to this point, the project has been conceptually defined, and the proposals have been request for proposal has been sent out. Multiple companies have responded, and one or more contractors have been chosen to actually execute the project. Go ahead and design the spacecraft, and then build the spacecraft, and then test it. So the full scale development phase, therefore, is the most important phase, and it's the what we actually will see the spacecraft being constructed. So first, we do have the preliminary design review. So once the contract is awarded, then there is a period of time, let's say 1 year or half a year, 6 months or less or more, through the preliminary design review, PDR. So design review is where the representatives of the contractor and customer sit together and review the preliminary design. So during this phase, so the design process starts. So the emphasis during this phase is still at the system level. System level means that looking at the big picture. Since it's still the preliminary design review, so very detailed analysis of each component is not necessarily done at this phase. So it's the system level to make sure that the system as a whole will work and how it's going to be designed. So the spacecraft design is still flexible during this phase before the PDR, and significant changes in configuration, payloads, and subsystem design should be expected. So even though the spacecraft shape is known, the different subsystems are known, but there is still flexibility in changing, all of these subsystems. Because in the previous phases, like the concept design, there was no detailed analysis, so everything was based on parametric study. So in this preliminary design review, still the design will go forward further, but still there is some level of flexibility. So doing so, being flexible, assist the system engineering staff and program management in defining an optimal baseline spacecraft design before the PDR. So this is like the optimization process. Optimization is done around some major defined point. You have to be next close to that base point, but you can go a little bit, left, right, up, and down in order to reach the optimal design. So that's the concept of the design of experiments, for instance, to find the optimal approach. So at this stage, any potential technical or development problems should be identified and addressed. If any problem is not captured at this moment and at this stage, later it may be too late. And usually meetings with other subsystem owners is important to share the results and press for changes among different subsystems. So different, like the thermal and structural and mechanical and electrical uh, system leads, subsystem leads frequently meet in order to communicate their progress and then ask for instance, changes in another subsystem if possible. So, for instance, the structural subsystem may feel that they would need a stronger or thicker, for instance, plates to support, the rest of the spacecraft, and therefore they may need more mass than what is actually in the document so far. So if one subsystem needs more mass, then the other subsystem owners should work with the other subsystem owner in order to reduce the mass of their own subsystem to allocate more mass to the one that actually needs more. So prior to PDR, preliminary design review, if you want to look at the thermal aspects, so these are the key requirements, and thermal design solution must be identified before the PDR. So the range of the mission orbits. So for instance, what is the range, if it's like a satellite, what is the range of the orbits of the satellite from like the parking orbit, like from launch phase to the final operational orbit? What is the range? Is it gonna go to the moon? What's the range of the mission? Because all of these ranges will affect the thermal load, and based on that the thermal solution will change. So for instance, a satellite, which a satellite designed for geo orbits, geosynchronous orbits, cannot all change, the orbit become like a LEO or MEO orbit, because the thermal uh, designs for these may be different. The period changes, and the period of eclipse changes, and so on and so forth. So normal attitude of the spacecraft, is it facing what the spacecraft, the satellite, is going to facing what part of it is facing the sun, what part of it is facing the earth, and so on. Launch phase configuration, so how it's going to be launched, because during the launch very strong mechanical and thermal loads are exerted on the spacecraft. Ground cooling needs, whether it needed to be cooled or kept at the right temperature when it's on the ground, and some other aspects like the failure, so how to approach the problem during failure. Temperature limits for different components, reliability requirements has to be defined, equipment power dissipations and operating modes. For in this stage, we should actually know what is the equipment power dissipation of each electronics, because we are going to, because at this stage we need to know the thermal load, which means the heating load and cooling load. So we need to know the power dissipation of each component. The launch system interface, so how the launch rocket is going to interface with the spacecraft, because the spacecraft is carried by the launch vehicle. So what is the thermal interface between these two? And also we need to know the interface between all different subsystems. So the interface between different subsystems means how they are going to interact with one another, different subsystems, and how, for instance, heat is going to be extracted from a different subsystem to the, for instance, radiator. So that's the interface. And also special thermal control requirements for some components such as batteries. Some components are very critical, such as batteries need to operate at a certain temperature range. If the temperature becomes, for instance, in the case of batteries, thermal runaway and probably failure of the battery and spacecraft can occur if the temperature goes above a limit. So some particular subsystems and components need to be considered carefully. Also, prior to PDR, to support the selection of a preliminary thermal design, the contractor is expected to provide trade-off studies addressing the degree of active versus passive control. So as I mentioned before, it is important to actually use passive systems. Now, if the contractor wants to use active systems, like if the contractor wants to use a mechanically pumped fluid loop instead of heat pipes, then they need to provide trade-off studies to basically demonstrate the need for more complex active systems instead of simpler, cheaper, usually cheaper passive controls, systems. Also, if the contractor wants to use deployable radiators versus fixed radiators, they need to provide trade-off studies to demonstrate the need for deployable radiators. Deployable radiators, if you remember, like the radiators which are unfolded. So of course they are actuated. There is a higher risk of failure. So if needed, then it has to be proven that they are needed. The PDR documentation should provide a complete description of the design, including the assumptions, even if it's preliminary design, but these are already needed. Key assumptions, radiator areas, insulation requirements, thermal finishes, coatings, their assumed optical properties, heater size and locations, heat sinks, heat pipes, if heat pipes are used, sizes and locations. So this is like a real design, but it can be further improved in the next step, and it can be further verified in the next step. So a flight instrumentation list and power requirements, because this is needed for the thermal load and cooling load, and a schedule for all thermal analysis and testing, which is going to be done in the next phases, should be presented as well. So then the PDR, which is the preliminary design review, is a meeting. It involves the contractors, specialists like the thermal lead and leads of our other subsystems, system engineers, program managers. They will meet with the customer personnel and their technical advisors. So to make sure that they are both on the same page, and to make sure that the customer agrees with what the contractor has been done so far and what they are going to do next. So during the review, the design is critiqued to identify any weakness in the design early enough, and criticism should not be taken personally. Criticism is actually not about people or not about engineers, it's about the design, and the objective is to make sure that it will work properly. And concerns, recommendations, and action items generated in the PDR should be carefully considered and should be addressed so that in the future problems will be prevented from happening. So once the PDR is done, then the next step, CDR, the critical design review, starts. So that this period is the term when most of the design and analysis work takes place. So now during this step, all of the details of the analysis will be done to make sure that all numbers and calculations make sense. Engineers should be able to demonstrate that they are on the right track to deliver a high quality product based on the following design criteria. So there should be no single point failure. So the design should be fault tolerant. It means that if something happens, something fails, if a heater fails, then a backup heater will come to the circuit. They should demonstrate that, well, and you may say that, okay, well, how about if the second heater fails as well? Then that's based on the requirement of the design. So what is the level of the reliability, whether you want 80% reliability, 99%. So that has been defined in the requirement, in the in the system requirement review. So reliable and flight proven, they need to demonstrate that. They need to demonstrate that the system that they are designing is predictable, their behavior is predictable by thermal analysis and verifiable by ground test, because this has not been constructed yet, right? So at this stage, it's basically calculations and perhaps some development tests for if a new solution is going to be used. So they need to demonstrate that later they can actually test what they are designing for the spacecraft, and they need to provide adequate thermal margin according to the standards, and the solution should be insensitive to the space, ground, and launch environment. So if they need to provide a level of sensitivity, if something changes, how adaptable the solution will be. They need to consider the corner cases that we have talked about before, the most critical cold and hot cases. The thermal solution should be able to handle those corner cases, and the solution should satisfy standards such as NASA or equivalent standards, and should be readily integrable or integrated. So let's say if so the thermal solution should be easily integrated with the rest of the spacecraft, and that's the case for all other subsystems as well. So if, for instance, you come up with a thermal solution that cannot be easily integrated and manufactured, then that should be addressed as well. So from the critical design review to launch, so this period is generally devoted to making any design changes dictated by the outcome of the critical design review, again between the customer and the contractor, conducting subsystem development tests. So if development tests are required that hasn't been completed before, so they have to be completed now, subsystem development tests. And building the spacecraft and testing it. So each subsystem has to be built because it's been designed so far. Now it's the time to build and develop the subsystems and then put them together and test them. Regarding the thermal part, the thermal hardware must be specified in detail and manufactured and procured. And then once the thermal hardware has been procured, the thermal balance and thermal vacuum tests must be planned and executed. So we do have a lecture on the thermal balance and thermal vacuum tests. So the thermal control components should be tested in thermal vacuum chambers and also even the entire spacecraft should be tested in the thermal vacuum chambers. So the thermal balance test is the critical verification of the thermal design. So we need to demonstrate that each component can operate at at the actual temperature and pressure of the space in vacuum and at the given conditions. That's for the components. And then the thermal balance test will show that when all of these subsystems interact with one another, they will be balanced. They are thermally balanced, meaning that it will show that the thermal solution is adequate and can actually manage the corner cases. So this will be done during the CDR to launch stage to make sure that everything that has been designed is built and is tested and it works properly, because after launch there is no way to fix problems. Oftentimes, once the spacecraft is launched, there is no way to fix it except for some like manned missions where the astronauts can go and fix things, but it costs a lot of money and effort. So before the launch, it's made sure that actually everything will work perfectly. So then the last phase will be the operation phase. So once the spacecraft has been launched, that's the operation phase. The work doesn't stop here. During this phase, the main duties is for the operation phase, it's launch preparation, launch support, and performance monitoring assessment. So it's like the launch itself and after launch. So if any anomalous performances or failures in the thermal subsystem occur, then the thermal engineer performs analysis to determine what caused the problems and what corrective actions should be taken. So let's say the spacecraft is like in the orbit, it's continuously monitored. If something goes wrong, then it may be possible to actually fix it. For instance, by restarting the system, by like a troubleshooting procedure, by writing a new code, by things like that, if possible. Also, it's important that if additional spacecrafts are to be built for the same mission in the future or for other missions, then the design changes may be needed to be investigated so that the same problem will not occur in the future missions. So in summary, during the operation phase, the thermal engineer should monitor, like all other subsystem owners, they should monitor the performance of the spacecraft in order to learn lessons from the mistakes and get data and analyze the data in order to improve the design for the future missions, and also to fix and troubleshoot problems from the mission control unit if possible. So this brings us to the end of this long lecture. So this is pretty much equivalent to two lectures in the class, or it's equivalent to 1 week of lecture. So we talked about different phases of design process. It was tailored for a spacecraft, but it's applicable to other engineering projects as well. So it will actually give you a broad understanding of what's going to happen in real world when a project is going to be kicked off and executed and then put in operation and so on. All right, thank you very much for your attention. Please make sure to watch the video more than once. There's a lot of stuff there, and also feel free to send me questions, comment in the comments of the video, or in the course website, or by email. and to make sure that everything is clear. All right, thank you, and we'll see you next time.